So, work package 1, it's Professor Maxim Kovalenko from ETH Zurich and from the EMPA. Claire Vilvier from PSI is the PI for work package 1-2 and Katharina Fromm, Professor from the University of Fribourg in Uchtland is work package leader for 1-3. What we do, according to the original plan we submitted, work package 1.1, oops, it's again the wrong bottom. So 1.1 should focus based on the original plan on lithium-ion batteries, 1.2 on sodium-ion batteries, and 1.3 on post-lithium-ion batteries. When you do a project application, everything is easy. When you start to collaborate, you see that there is much more overlap than you believe at the beginning before you started. In fact, we have expertise in the synthesis of electroactive materials, in the characterization, electrochemical analysis, and understanding of reaction mechanism. And we realized very soon that this is, of course, independent on the system you are looking into. So, in fact, we have a situation that there is a lot of overlap between the different work packages, and it is the intention of the SCCR, and we are so far that we decided to work together, all three PIs, on all the three different topics, in the sense that we have here more or less the expert in the synthesis and coating, and we have on the other hand, here, the specialist in electrochemistry. So this is how we look into the problems right now. The target is for all the three PIs, all the three groups to contribute to the development of better batteries, which could be based on lithium, sodium, magnesium, whatever you will like for the future. So we developed a common approach for the batteries, for the synthesis of the materials, which is mostly done by Kovalenko's group, and for the cathode materials by Katharina Fromm's group, improvement by coarser synthesis, special carbon coatings, and so on. Rough electrochemical screening is done at these two different locations, and at PSI, in the group of Claire Vilvier, we concentrate more on the characterization, understanding, and on developing good feedback for the guys that are doing the synthesis. So at the end, we have something which I would call the pre-demonstrator. So when I will finish my talk today, I will show you some results on full cells, and I will concentrate today on the new challenges in sodium-ion batteries. So it is just one part of what we are looking into the work package 1. This is a joint work between the three groups, and the first question I will have to answer to you is why we take care of sodium batteries. The question why lithium batteries is hopefully not necessary to ask for, because every one of you will have at home here roughly 10 to 15 lithium-ion cells, perhaps 20 now. That's if you don't know, look what you have in your laptop, what you have in your mobile phone, and what you have in your tablets, computers, and eventually in your car if you are running electrically. So when you look, lithium is working well, it is small, sodium is bigger. So should it be better? Actually, when you look on the basic data, everything seems to be worse. The lithium, the ionic radius is getting bigger, the molecular weight much higher, the potential more positive, so we are losing energy. So the theoretical capacity, which has nothing to do with the voltage now, it's just the capacity is 3 times less than for the lithium. So on the first glance, I would say sodium is not necessarily the best solution. The question is, does size matter? I would say yes, it does. I like it big. But these are the previous data. So the green is, we like it. It is smaller. However, there is much more sodium than lithium. I am very often confronted with the question, is there enough lithium? Yes, there is enough lithium, even if we don't have the lithium physically available in mines, because there is enough lithium available for all the lithium batteries, future batteries in seawater, and the technologies are already developed to take it out. It is just more expensive. So the problem is not the amount of lithium, the problem may be the cost of lithium compared with sodium, and this is current cost, so probably this one would go up. But there is one issue which is not so visible. Someone told me, Nigel, thought it, if people are investing into copper, they want to keep it running for 40 years, whatever. Copper is expensive, and we have a lot of copper in the lithium-ion batteries. This is what is not visible. The copper is expensive, and there may not be enough copper for the future batteries. The copper is used as the current collector. So the main advantage, while we are looking into the sodium-ion batteries for the future, in respect to cost, is the possibility to replace the copper current collector with aluminum, which is much cheaper, and much more aluminum is available. There is another one, is of course, this is the risk of supply of lithium. The technology is known, but there is a risk. There is no risk in the supply of sodium. So how the sodium-ion battery works? In principle, it is the same system, the same chemistry, we would say, as the lithium-ion battery. We have a positive electrode, which is actually sodiated at the beginning. We have a negative electrode, which is based on carbon, which can accommodate the lithium ions. We have the electrolyte where the sodium ions are moving, and we have the SEI on both kinds of electrolytes, SEI, SPI, whatever you like to it. It is a protective layer which will create both the desired properties of having a barrier between the electrolyte, which is thermodynamically unstable, and the ionic conductivity, which helps. At the same time, it is increasing the resistance on the surfaces, and it is decreasing the power. On the positive electrode, we have something similar, where the reason why we look into this is that these layers on the positive electrodes are increasing the impedance, so decreasing the power. So if you know the picture of the lithium-ion battery, you will probably notice that in the lithium-ion batteries, the graphene layers are nicely parallel. This is because graphite is used. Graphite does not work in sodium batteries because the potential of the deposition of metallic sodium is more positive than the potential of sodium intercalation into graphite. So this is disordered carbon, which implicitly tells you another disadvantage we will have to solve. This is the low volumetric energy density of the negative electrode. The disordered carbon is accommodating less sodium than graphite, could theoretically do, and the density of the electrode is much less than the 2.2 for the graphite, which is a crystallographic energy, crystallographic density. So the gravimetric energy density is one thing. The volumetric energy density could be compromised here. So what I will tell you is what we are doing within the work package 1 in the field of sodium batteries. I will show you one story from the electrodes, from the material to the small demonstrator. Please keep in mind that there are further activities, so the lithium, post-lithium, and so, which are not included in my talk. I will start with a kind of electrode engineering, tell you something about the selection of the electrode, and especially give you the reason why we decided not to work with the carbon, which has the low volumetric energy density in theory, and we are looking for materials which can give much higher energy density for the system, and then I will go to the positive electrodes and the full systems. So, which kind of materials can be used in sodium-ion batteries? In principle, everything what is available, the chemistry will offer. It is very similar to the lithium-ion system. So for the positive electrode, we have a bunch of options, materials inserting, intercalating sodium. All of them are in the order of 2 to 4 volts against sodium. So we will have a cell with a voltage between 2 and 4 volts, probably not more. For the negative electrode, if we will not keep the metallic sodium, which does not cycle well, we can work with the carbon, but we can also work with the alloys. The highest energy density would be theoretically done with phosphorus, but we decided to work with tin, antimony, and so on, from the reasons to have something which is workable. And of course, at the beginning of the project, we believed that we will take our knowledge, 20 plus years knowledge of lithium-ion batteries, and we can take it almost 1-to-1 to the sodium-ion battery. And what we learn is this is not so true. So we use the standard electrolyte formulation, and I want to focus your attention to the binder, which is actually an inactive part of the electrode, which is there just to put the particles together. And the polyvinylidene difluoride is a standard binder for lithium-ion batteries, works well. So this is of course obvious to take it and look for something which is very similar. There is no reason to think that it should be different. And we found out it is not cycling well. So when we change the binder for the tin electrode, so this is the alloy, which has a very high volumetric energy density, we got much better cycling. It is still not the best one, but I want to stress what we are doing now in the first and second year is to identify the problems to work on. Don't expect from us that we will be able to have an industrial ready battery in 2 years. So the binder is a problem. We were looking how to understand this. The first take-to-home message is the know-how from lithium-ion batteries cannot be applied to sodium-ion batteries 1-to-1. And we were now looking further. So another example for lithium-ion batteries, the standard electrolyte salt is LiPF6, which is dissolved in a mixture of carbonates like ethylene carbonate, dimethyl carbonate. If you take the sodium equivalent, it does not dissolve good enough to get at least something which is close to the 1 mole. So it's another no-go. So in the literature, they work with sodium perchlorate. We do as well. We are aware that in small tests it works well. For an industrial battery, we will have to look for something else because people do not like the perchlorates in big amounts with the combination with organic materials. We have the propylene carbonate as the solvent, and based on the literature data, we are looking on the influence of the so-called FEC fluoroethylene carbonate, which is a good additive to form the SEI for the lithium. So what is the consequence on the electrodes interface? This is the first question to be answered. Is the interface a problem? Yes, we learned interface is a problem. So we were looking with XPS, and what we learn is, well, for the pristine, if you have this PVDF, which does not work so well in the sodium-ion batteries, we have the formation of sodium fluoride. So you can have a look. We have it here. This is, of course, clear that the binder is decomposing much faster, but we have much thicker SEI. For those that are not familiar with the battery business, the SEI state for the solid electrolyte interface. This is this surface layer which is actually protecting the thermodynamically unstable electrolyte in the kinetic manner to react very fast and to decompose. So, what we learned, PVDF is decomposing in sodium-ion batteries, but the FEC can prevent the decomposition. Then we look on the bulk, what the material is doing. We have still the tin, which is the alloy. We know that there is a volume change during the reaction with sodium, and don't be confused too much. The diameter here is rather symbolizing the volume of the alloys we are creating. We start with tin. There's of course no expansion. We have something intermediate, sodium tin 1:1. We have already 56% volume expansion. You go farther, you have 250%, and you end up, you can identify all the phases using in situ XRD. You can do it here at the PSI just across the road. We have roughly 400-something% of volume expansion, which of course is independent on the surface layer, so it is independent if you put the FEC into the electrolyte or not. So what does it mean? The underlying problem for the high energy negative electrode for sodium batteries is the volume change. We have the huge volume expansion, which goes to something which is kind of pulverization of the material, and of course we are then losing the electronic contact. The material is still there, but the material does not work properly during cycling, and this is the reason why you saw this huge capacity decay after few tens of cycles. So we have something which we call the dead material in the electrode. So we developed a concept based on literature how to mitigate this problem. We combine the active material which can alloy with sodium, and we combined it with inactive material like cobalt, iron or manganese. They do not alloy with sodium, so this is actually something like a pillars or stabilizing the system. But the idea is that this alloy will not change the volume during cycling so drastically. So the synthesis is done in the lab very easy by ball milling, which is a fast way. It can be transferred to the industry, it can be scaled up, but we have some disadvantages. In particular, we have now the wide particle size distribution. It is not so optimized. So what we have is a couple of alloys which are working and which are increasing actually the useful capacity during cycling. So iron, cobalt, magnesium. Why? We believe that at the beginning we have a kind of core shell reaction, but we still have some volume changes and cracking which are exposing more material which can be then more easily cycled. So there is a lot of differences between the alloys. We are going to understand them. So the real question is, we don't understand the reaction mechanism yet properly. And the question is there the transition metal which is extruded and which is then inactive after the sodiation? Why there is still differences after the 20 cycles and so on? So this is where we are at the moment. I am not giving you the answer to all of the stories. What I want to show you is a few another approaches in the full system. One obvious possible solution is to go for nano, and Maxim Kovalenko synthesized a nano material, nano tin, which works very well for lithium, but for sodium, well, it is an excellent performance, but the concept should be applied to the entire family. So what we have now from Maxim is, it is cycling. There is a lot of work to do. For the bulk, there is an increase of specific charge. When we go for the nano, there is a lower specific charge, which we believe is because there is too much surface which is exposed to the electrolyte, which is thermodynamically non-stable. So the conclusion here for this part, and I will be hopefully ready in a few minutes, because the remaining part is very short. Well, we learned that how to synthesize the tin-based material. The specific charge is there, but there is a strong fading during cycling, so we have to work on the cycling. And the question is it because of the surface layer and the surface in the batteries? So Katharina Fromm's group tackled this problem, and they developed a Yorkshire coating for both lithium and sodium inserting material, and we have now the materials in the lab. There is still a lot of work to do, but we have a concept how to mitigate the problem. So on the negative electrode, well, engineering is needed. There is a lot of problems. We will work on this. Target is, of course, the full cell. So we are looking for material for the positive electrode, for having also some voltage. And in fact, we are concentrating on two materials. So this is the cobalt-based oxide and the vanadium-based material. We synthesize all of them. We characterize them in respect to the cycling in the sodium cell. I want to stress these are the first material we selected, and we wanted to show the proof of concept to have something which works for the positive electrode. So the good news is, yes, it works. The bad news is there is still a lot of work to do in order to optimize to get the full capacity. So we have to improve the balancing, the potential window electrolyte formulation, but we have a full cell demonstrator which shows that the sodium ion battery concept is working, and we identified the problems we have to focus on in the future to come, hopefully, following our roadmap to the industrial type of demonstrator in due time. So the engineering needs to be improved, but we have the successful synthesis of the alloys for the negative electrode. The specific charge for the anode materials is, I think, very good for the starting point. We understand the role of the transition metals and want to understand in more details. The cathode improvement is in progress. We demonstrated the fuel cell prototype, and we submitted an SNF Synergia project where we hope that we will increase the manpower working on the sodium-based part of the work package 1. So thank you very much for your attention, and I would like to thank, of course, to the organization and companies. They contributed with money, materials, or both. Thank you.